Hello everyone. In this session, we will have a glance at the classification and control characteristics of some of the power devices that are commonly used. Let us start with the classification of the power semiconductor devices. There are several ways in which you can categorize the power semiconductor devices, and as you can see, some of these are listed as here. We'll start with the most basic one, which is the uncontrolled turn on and turn off. And an example for such a semiconductor device would be a simple diode. Now, the reason for being it called as an uncontrolled turn on and turn off is the moment you provide a positive voltage at the anode and a negative voltage at the cathode, a diode is forward biased and starts to conduct. And there is no other external parameter that would enable the user to control the turn on of the diode. A similar operation can also be used to turn off a diode. The moment the value of the anode voltage becomes either equal to or lesser than the voltage at the cathode, the diode would turn off. And that is why we call it as an uncontrolled turn on and uncontrolled turn off device. The next category we have is controlled turn on but uncontrolled turn off. An example for such a device would be a simple SCR, or thyristor is what is actually commonly called as. Now, as we know, a thyristor requires two voltages for proper biasing. One is a positive VAK, and the second one is a gate voltage, again positive, with respect to the cathode. Now, as we already have learned, the best way to turn on an SCR would be to give a nominal voltage across the anode to cathode terminals. It should be positive, plus give a positive voltage across the gate with respect to the cathode to turn it on. Now, when you want to turn on an SCR, as we know, the SCR would require a gate voltage, without which you can only turn it on by applying a very large voltage across the anode to cathode terminals, which is, as we already have discussed, a destructive phenomenon. So, the gate terminal of the SCR acts as the control terminal, and it is usually used only during the turn on process. So, the gate voltage will act as the control voltage and will help us in triggering the SCR during the turn on process. Whereas we call it as an uncontrolled turn off device because once the thyristor is on, gate has no control over the working of the thyristor, and whether you provide a continuous positive voltage, no voltage or negative voltage, it is not going to be it's not going to impact on the working of the SCR. That means the SCR will continue to be in the conducting state, and that is why it is called as uncontrolled turn off. The only way you can turn off an SCR is by making the current across the anode to cathode become lesser than a value known as the holding current of the SCR. Now, coming to the third category, we have the control turn on and turn off characteristic devices. Examples for these devices would be BJT, Mosfet, gate turn off, static induction thyristor, IGBT, all of them. Now, what actually is the characteristic of these devices is that they require continuous control voltage across their control terminals. For example, for a BJT, when it is biased in common emitter configuration, a continuous base voltage is required to keep the transistor in the on state, provided we already have given a positive voltage across the collector to emitter terminals. The same can also be said for a MOSFET, except that now we are providing the control voltage across the gate terminal. So, the gate and the base terminals of the MOSFET and BJT act as the control terminals of these devices, and that is why we call them as controlled turn on and turn off. So we actually must emphasize on the turn off also, because the moment you remove either the base or the gate voltage for a BJT or a MOSFET, the device will immediately go into the off state. Next, we have the continuous gate signal requirement category. in which you need not say it is gate signal, it can be continuous base or gate signal. Once again, the same BJT MOSFET can be used for this particular category as examples. Why? Because unlike an SCR, BJT and MOSFET require continuous voltage across their control terminals, whereas an SCR only requires a very small pulse of a finite duration to trigger it. And once the SCR is on, the gate, as we already have said, has no control over its operation, and therefore you can make the gate voltage 0. But the same cannot be said for a BJT or a MOSFET, because they require continuous voltage across their control terminals to sustain the device in the on state. So BJT, MOSFET and IGBT, they all therefore come under continuous gate or base signal requirement devices. Next is the pulse gate requirement. So we just discussed about this in the SCR category. SCR would not require a continuous gate voltage. It would only require a very small pulse at its gate terminal to turn it on, and after that you can remove the control signal, which is the gate voltage here. So SCR therefore can be categorized under a pulse gate requirement device. The same is applicable for GTO, which is also again a gate turn off thyristor, or a MCT, MOS controlled thyristor. Then we have a next category, which is the bipolar voltage withstanding capability devices. Now, in the sense, we are not talking about the primary voltage here, we are talking about the control voltage. So here examples for these devices are SCR and GTO. Now, what actually is bipolar voltage withstanding? This means that the device can withstand both positive and negative voltages across its control terminal, which is here the gate. So whether you provide a positive gate voltage or a negative gate voltage, once the device is on, it is not going to put any impact on the working of the device, and therefore we call it as bipolar voltage withstanding capability device. Then unipolar voltage withstanding. That means the device can only take one type of voltage across the control terminal, and reversing this voltage or applying a negative voltage across the control terminal is going to produce a misbehavior by the device. For example, a BJT, MOSFET, GTO, IGBT, MCT and all, they come under unipolar voltage withstanding capability devices. That is, for a BJT, if you want to turn on this device, you can only apply a positive voltage across the base terminal. You cannot apply a negative voltage, because by applying a negative voltage, you are going to send the transistor into reverse conduction mode. Similarly, the same principle is applicable for MOSFET also. Obviously, we have multiple types in a MOSFET, but every MOSFET, whether it is enhancement or depletion, N-type or N-channel or P-channel, it is very specifically set that a certain voltage of a given polarity only should be applied across the gate terminal of the MOSFET. And coming to the next category, we have the bidirectional current carrying capability devices. As the word itself is very clear, this means the device can carry currents in both the directions. That is why the name bidirectional. An example for this would be triac and RCT. RCT is reverse conduction thyristors. A triac would be a very illustrative method of understanding a SCR. That means you have to simply connect two SCRs connected back to back, but with the gate terminal shorted. So both the SCR devices, gate terminals of the SCR devices are connected as one single gate terminal to create an SCR. To create a triac. Here, the current carrying capability is both from anode to cathode and cathode to anode. Though we do not say these are the terminals of a triac, but when you connect two SCRs in an anti-parallel connection, you can imagine conducting the devices in from anode to cathode for the first device and from cathode to anode in the second device. So they can carry current in both directions. And quite obviously, the last category would be unidirectional current carrying capability devices. So most of the other devices what we have in the list do come under the unidirectional current carrying capability devices. For example, in SCR, conducts current only in one direction, that is from anode to cathode. So is the case for most of the other devices available in the list here, for example, a BJT, Mosfet and all. They conduct current in only one direction. The current cannot flow from the other direction. For example, for an SCR, the current can never flow from cathode to anode. And that is why we call them as unidirectional current carrying capability devices. So this was about the classification of power semiconductor devices. We will continue our discussion, and we will go to the control characteristics of some of the power devices that are very commonly used. The power semiconductor devices can be operated as switches by applying control signals to the gate terminal or base terminal of thyristors or BJTs respectively. Now, the required output is obtained by varying the conduction time of these switching devices. Please note, if you want to obtain a certain voltage at the output, you can produce the same, or you can attain the same by controlling the turn on or the on duration of the device by triggering the device at a value you would like to have. So the depending upon the power requirements, ratings, fastness, and control circuits, circuits for different devices can be selected. So here we are going to illustrate the control characteristics for very few of the very commonly used power semiconductor devices. Let us start with a simple thyristor switch. So here you are looking at the thyristor, and we are expecting a load voltage connected across a simple resistive load, and the input voltage is given as Vs. Now this is supposed to be DC. Now if it is, even if otherwise it is AC, the thyristor will go under normal commutation. So for this illustration, and as you can see, the output voltage is constant at Vs. You must understand this is a DC input source, right? So when you apply the DC voltage across the VAK, the thyristor will go into forward blocking mode. In the sense, out of the three junctions, junction J1 and J3 of the thyristors are forward biased, but junction J2 is reverse biased, and it is expecting some gate voltage to be given across the gate to cathode terminus of the thyristor, and that is where the control voltage or the gate voltage comes into picture. So here what we have done, we have given the gate voltage at exactly time t is equals to 0, and that is the reason why you are getting an output voltage starting from t is equals to 0 itself. If instead I had shifted this pulse to a little right, then you can only get the output voltage from the instant at which the gate voltage is applied. Now, once the gate voltage is applied, you see the gate is only of a pulsed type, not a continuous one. But still the thyristor continues to be in the on state, and therefore you are obtaining a output voltage which is equivalent to the input voltage under ideal conditions, because ideally there is no thyristor voltage loss or there is no ohmic drop across the thyristor. Now, interestingly, we have a second gate pulse which is very similar to the first gate pulse, and this is given after a finite amount of time. However, as you can see, there is no impact of the second gate pulse because the thyristor is already on and latched, and once the thyristor is on, gate has no control. And even if you provide a negative gate pulse, as you can see here, the output is still going to be the same. So the gate voltage is only used for turning on a thyristor, and once the thyristor is on, gate loses any control over the thyristor and the thyristor continues to conduct. And now this has to be noted because it is only for DC. If the input were AC, the moment the positive half cycle ends, the voltage VAK becomes negative, which voids the primary voltage requirement, which is a positive VAK across the thyristor, and the thyristor is said to be naturally commutated. But a student should, whenever asked for control characteristics, write this particular with DC input voltage source. Now let us go to the next one. Here we have three different devices: static induction thyristor, we have a gate turn off thyristor, and finally we have a MOS control thyristor as well. So for all of these devices, the same the same waveforms are going to be applicable. I will take an example of a GTO for illustrating this operation. What we have done is we have simply changed the thyristor with a GTO. Okay, so input is still DC, but if you look at the gate terminal of the sorry, if you look at the gate terminal of the GTO, you will see there are two different lines with arrows indicating one towards the gate terminal and one inwards the or towards the SCR. Now, what this means is that this device, which is our GTO, responds to both positive and negative values of Vg. That is why you can see Vg, both plus and minus are indicated here. So let us go to the characteristics. Once again, we are going to apply a gate pulse exactly at time t is equals to 0, and at that instant the SCR starts to conduct and you would obtain an output voltage equal to input voltage under ideal conditions. So this is what is being shown. But after some time, as you can see here, we have a negative gate pulse to applied at the gate terminal of the GTO. Now since GTO responds to both positive and negative gate pulses, immediately this gate pulse is going to turn off the GTO and therefore this becomes open and the output voltage becomes 0. So that's why from T1 till the next gate voltage, which is positive, is applied, the thyristor will be in the off state. So this is the control characteristics of GTO. The same is applicable for SITH and MCT as well. The third device we have at hand is the transistor, very commonly called as BJT. Now, once again, the input voltage source is DC, we have a resistive load, and we are going to provide a positive voltage across the base. That's why the symbol plus here, and it has to be positive because the device is not going to respond for a negative voltage and not suitable or not suggested as well. So the moment you provide a positive base voltage, the device becomes a closed switch and an output appears across the load. And that is why this is a control voltage. We have not shown the supply voltage in this one. So we have the base voltage applied across the base to emitter terminal of the transistor. And as long as the base voltage is applied, you will obtain a output voltage across the load. The moment the base voltage is removed, the output voltage becomes 0. And the voltage will only become positive again when there is a next positive base voltage applied across the base to emitter terminal. That is why we call this as a continuous base or gate requirement device, whereas the other one, the previous one, this does not require continuous gate supply or voltage because it is a pulsed gate drive device. Coming to the last one, we have Mosfet, also IGBT. Now why we can use these control signals for both MOSFET and IGBT because the control terminal of both these devices is the gate terminal. Though IGBT has a different set of terminals when it comes to the other two, as we can see, this has a collector and an emitter. We already have seen in our previous session that IGBT is a combination of a BJT and a MOSFET. It borrows collector and emitter terminals from the BJT and gate terminal from the MOSFET, and that is why it is called as insulated gate but bipolar transistor. Right, now coming back to the characteristics, input supply is once again DC. Now when I provide a positive VGS voltage from gate to source, the MOSFET closes, it acts as a closed switch and an output voltage appears across the resistive load. Now as long as this VGS is positive, the load voltage will continue to be equal to that of the supply. The moment the VGS is removed, the load voltage becomes 0, which is very similar to what we have seen in our previous diagram also, which is for the BJT. Right. So this is about the control characteristics and classification of power semiconductor devices.